Okay, good morning. This is webinar number 2 of the day of our bi-monthly webinars. This one's on innovations in decommissioning Chalk River Laboratories reactor support facilities. Before we begin, CNL respectfully acknowledges that the CRL site is located on the unceded and unsurrendered territory of the Algonquin and Anishinaabe Nation. We recognize and appreciate their historical connections to this land, and as the customary keepers and defenders of the Ottawa River watershed and its tributaries. We also recognize and appreciate the contributions that all First Nations, Métis, and Inuit peoples have made and continue to make in shaping this land we now know as Canada. We acknowledge, respect, and seek to better understand the unique Indigenous history, rights, and title on the lands where we work. Before we kick off today, there is simultaneous interpretation of this discussion. If you can access the session in French through the globe icon on the bottom right of the bar on Zoom. Today's session is planned for about 45 minutes. We'll do a Q&A at the end. You can submit your questions with the Q&A function, the Q&A icon on the bottom of your screen. Note that we do record these sessions because we post on our CNL YouTube page afterwards. If you experience any technical difficulties, please email ermstakeholder@cnl.ca. We'll try and get you figured out. We are also trying to evaluate our webinars more in depth. So following the webinar, we do have, you will receive an email with a link to complete a short 10-question survey. We'd really appreciate it if you would take the time to share your thoughts. Leading today's presentation is Patrick Mansfield. Patrick is Chalk River Lab's Project Director of Decommissioning Program Execution. He's been with CNL for over 16 years and currently oversees the decommissioning efforts of multiple legacy buildings across the site, including but not limited to the reactor support facilities we'll be discussing today. Patrick, over to you.
Good morning. Thank you, Mike. I appreciate the introduction. Again, as Mike said, my name is Patrick Mansfield. Looking after various portfolio facilities here at Chalk River, focusing on some of our reactor support facilities and operating labs. But today, I'm happy to share and talk to you about innovations in some of our recent decommissioning activities. We'll do a bit of a history on Building 204. Building 204 was designed and constructed in the mid-1940s to provide the storage, handling, and processing of fuel rods from the National Research Experimental NRX reactor. That began operation July 22nd, 1947. NRX was used for nuclear physics research, medical isotope production, and the testing of reactor fuels and materials. The main purpose of these bays within 204 was used for fuel examination and storage while providing cooling and shielding of the fuel. Fuel rods were removed from the reactor, discharged in a series of bays. The rods were held in the bays for roughly a minimum of 6 months to allow for a cooling period, and then transferred to a series of bays and to dissolvers located in the adjacent buildings, where they were processed for items such as plutonium and uranium recovery. So what were things that happened in 204? What did 204 do? So it was constructed to support the operation of NRX and later on supporting NRU, where spent fuel rods and irradiated materials were processed underwater along 150-meter long trench and base system to shield workers against the high radiation fields from the fuel themselves. The water in these original 5 bays contained roughly around 2,000 cubic meters of water, which over time during processing became contaminated. Then was clarified and filtered to reduce turbidity, concentrating radioactivity contaminants with infiltration equipment in what's referred to us as the Bowser room. An isolation bay was installed as an addition in 1954 It allowed for process failed fuel rods from the 1952 reactor accident that happened in NRX. The isolation bay allowed for rods that were traditionally stored in next rod bays to be removed and separated for further handling and examination due to the impact from the event itself in 52. In 1957, reprocessing at the Talk River had ceased, and the bays underwent extensive modification and reconstruction from 1959 to 61 to support other initiatives at CRL. The examination bay, which is called the uncut rod bay, was separated into a water-filled bay for rod examination to support R&D initiatives, as well as a second for fuel storage from the nuclear power demonstration reactor, which is located north of Chalk River. The J-rod bays, which were originally used to process J-rods for uranium extraction, was modified and divided into two deionized water reservoirs, which were critical for the supporting both NREX and NRU's operation up to shutdown. The X-rod bay was used to process fuel rods destined for plutonium extraction, but post-1960 were never repurposed. These processing capabilities from the B204 bays enabled vital research in materials and science and fuel design, leading to advancements in Canadian nuclear technology for both energy and medical applications. So preparing for decommissioning today. Since the end of our operations, we went through many decontamination campaigns and characterization campaigns to provide the project with some of the information we have to date and the condition of the facility that we have to date. Thorough cleaning campaigns were underwent in the early 2000s on the bottom of the bays, rod bays and floors. However, still after a lot of effort, contamination is still in the system. Findings from the team were, dose rates were still evident and proved to be a challenge for the bays and the surrounding areas. The Bowser room, which I mentioned, which was the filtration room for the water cleanliness of the bays, had many maintenance challenges during its life, resulting in risk for contamination and high radiation levels for certain components of piping that remained within the room. Similarly, the radiation fields in the isolation bay were, quite high in dose rates as well as a result of their own separate filtration system, which took the isolation bay water and ran it through a separate filtration system so it wouldn't contaminate the other rod bays when they were working on those damaged fields from 1952. Other key enabling activities for the safe decommissioning included removal of legacy utilities, the installation of new temporary systems to get ourselves off of site systems protecting our workers, set up a significant field trailer for our workers to assemble and deploy each day, and procurement of various innovative equipment for helping us access these high-risk areas. So what have we learned to help us inform the plan and execution activities that are currently underway or have been completed in the past? So through characterization, we gained essential data to facilitate safe and effective disposal of legacy equipment and systems. The use of robotics in high-risk areas, like the water filtration room, which I mentioned is the Bowser room, has proven to be, optimal methods to mitigate contamination risks and minimize radiation exposure to our personnel. Surveys have proved critical insights into stabilizing concrete structures, which pose an increased hazards if we remove the systems entirely. Furthermore, the team made attempts to decontaminate these walls, but found them practical, guiding us to develop more efficient and risk-informed strategies for placing the facility in a safe interim state before a further decommissioning campaign happened. Execution of these legacy work plans within the facility created a valuable database of lessons learned for us, which the team have used to streamline and improve the planning process, specifically around, we start with smaller, low hazard activities or tasks and move our way into higher hazard activities and tasks where we can build up that confidence and those lessons learned to apply to future plans. So I want to take a second to really highlight some of those major challenges where the innovation piece comes back in to help solve some of our problems. So I mentioned historically and from some of the characterization work we have completed, we do have quite the amount of high radiation dose rates coming from some of the systems as well as the bays themselves. So that led us to look at, what equipment could we seek in the industry that is innovative, that would remove the worker and basically become a remote tool. Next were high radiation dose rates in systems. So upon completing surveys using remote equipment, how could we remove these systems without introducing workers in full dress PPE versus utilizing robotic equipment? Contamination control was a known challenge. We needed to ensure we contain contamination and protect both the facility, the workers, and the environment. So we needed to consider alternatives for remote fix of systems. We also needed to come up with ways to verify that our fixative applications met the intent or the purpose that we were targeting to hit. So we needed a way to verify after the application of such fixatives if we achieve the appropriate thickness and the appropriate intent. This is where we also looked into alternative surveying equipment. Finally, we realized that we need to shield and compact certain granulars or aggregates within the bays in order to allow for future activities here to happen in support of our demolition. So we looked at, again, remote equipment, which we'll touch on the upcoming slides. So taking a second to talk about the Bowser room. So talking about some of the problems we identified and how that informed our planning. So historical data revealed that a process equipment was highly contaminated, and particularly our filter packs, valves, pumps, all the plumbing had significant levels of contamination that was identified through some of our early entries in full air-fed suits. Due to this extreme contamination, doing invasive characterization work and removing these system structures wasn't really deemed to be practical. The complexity of removing these structures without releasing further contamination posed additional risks as manual removal in these confined spaces, which was in the location of these pumps, valves, was in the basement, heightened the chance of puncturing and tearing our PPE, which required obviously removing staff immediately from a confined space, which is a known challenge. So to construct a safe and efficient access point without having to utilize it as a confined space, we positioned fully equipped, designed C-cans outside the room adjacent to the basement, creating the controlled entryway. The team cored an opening from one of these C-cans into the physical basement of the Bowser room itself and established a secure passage that enabled the entry of a Brock robot for remote operations. Brock is a name brand. I'm going to use it consistently throughout the slide, and they provide us with a robotic mini excavator, which we'll see in the upcoming slides. These seed cans served as waste processing facilities. They allowed us to handle and process the waste materials in a more controlled manner with less direct human exposure. Given the high contamination levels, this setup enabled the safe remote removal of the waste and significantly reducing radiological risk to personnel. The plan phase involved collaborative development meetings with our field technicians, our subject matter experts on site, from health physicists to past workers and operators from NRX, engineering teams, and of course our innovations. Next slide, please, Mike. So we're going to run a short video here to show you single-handedly the work that was performed. But what's going to showcase first is the work we did to prepare the site and make access into the basement Bowser room by deploying the CCAN, which was a ventilated enclosure and safe handling location for the workers to not only work on the Brock and equipment, but to handle the waste and package it appropriately. Here you can see the congestion of the room and how difficult it was to consider deploying a crew of field staff to manually remove some of this equipment. The Brock and the equipment itself is very efficient, works quite well in these high radiation fields, and is all done remotely. So staff are essentially in a control room with live video feeds, as the Brock itself has camera heads on it, in order to remove the equipment and get us to a point where we then have applied a CC fixative. And here we can see sort of a 3D rendition of us backing out of the Bowser room, empty, clean. As we sit today, the room itself is completely empty. All the pipe stubs have been cut to the concrete and foamed, and all the waste has been appropriately packaged to our waste management plans and are destined for our appropriate waste locations here at Chopper. So the isolation bay room, it also posed a significant challenge to the team. So what did we find and what led into the planning? The recirculation system in the basement isolation bay, as I mentioned previously, allowed water within that isolation bay to recirculate on its own without drawing and cross-contaminating the water within the room unit of the bays. So we knew not only the isolation bay itself from the history required the need for decontamination, but we also knew that the systems itself need to be appropriately removed. Some photos here on the right are showing some scanning we did with remote probes, and our innovations team helped here to highlight some areas where the piping itself was a lot higher dose rates than other locations. So it led us to believe that we might have some remaining particulates stuck in legs of the piping system that need to be handled outside of probably traditional worker involvement. This led us to develop work plans to cut and drain these systems in order to deploy robotic equipment. I'm probably getting ahead of myself here, and I'll get that to the next slide. So the video here, unfortunately, isn't going to dictate because we just finished the work very recently. So you can see here the rendition we did to inform our planning. It helped us define what locations we were going to sample, what locations we were going to cut, and what locations we were going to leave for the robotic equipment. The video here is showing some of our radiological staff using remote probing to trace along the piping system and indicate areas with significant dose rates. So since the crew has been in here and our innovation team provided us with that mapping of the high source areas, we mobilized a crew and a team. We completed our cold tapping, draining any legacy water, and foaming the areas that needed to be removed. The piping and pump system has been removed. We removed all the high hazard components utilizing the Brock remote equipment and the same grapple and shears. Since the removal of all the equipment, the lead has been appropriately removed and stored as a secondary waste, and the room itself has been applied with a coat of contamination fixative, similar to what we did in the 1000. Although we haven't completed measurement of these dose rates in the room since, we are very confident that the rates within these rooms will be drastically, significantly lower than they were before. So the A bays, which is a great look at that visual, that is looking right into the garage door of the A bays. Thanks, Mike. So we knew the A bays required sealing and shielding due to high contamination and dose rates. With the leaks in the bay walls making some decontamination impossible, the complex geometry of the space made it unsuitable for an automatic sprayer, necessitating the use of the Brock and remote camera inspections. The A bays were connected to the NRX building via an underground trench, requiring a physical barrier to prevent all the shielding material we planned to install to spill over into that same trench. So the team came up with a very creative military solution to utilize these barriers to seal off that trench location, so we were able to fill these bays. The large footprint of these bays required specialized equipment to access, but also due to the constraints of the location, we couldn't just utilize normal industrial equipment. So the team found an innovative option being a remote rock slinger to sling the gravel into these certain access points. The planning process involved aligning with interim end state by selecting a M25 polyurea resin spray, which applies about a 1/4-inch layer in these bays, ensuring a liner integrity through the product's rapid cure time and toughness. The field technicians supported us, were trained on using this Brock equipment and modifying the equipment to handle and mount this spraying equipment and develop techniques to operate it in these remote locations. As I mentioned before, we developed a remote viewing camera station on each one of these Brocks back to a control room in order for our staff to do all this work remotely in actually a trailer outside the room. So they're not even in the same room when they're performing these activities. Next slide, please, Mike. So how do we prep ourselves for these high hazard, high risk activities? We do what we call mock-ups. So the mock-up phase involves essentially evacuating a true size area of the bays themselves using heavy equipment to mimic the bay and the bay's layout, allowing operators to build experience and validate the approach for filling, leveling, and compacting. We use density gauge testing to conduct and correlate lift thickness and compaction passes to ensure we achieve the density required from engineering and provide crucial data to establish the work plan procedures for filling and packing these A bays. Remote spraying was also performed in the same location using the Brock and the remote Brock equipment mounted with the M25 sprayer on the Brock, verifying the approach and providing valuable data for the workers to feed back into the work planning team. So the picture on the bottom left shows us filling the hopper of the rock slinger, slinging rock into the mock-up bay where we have the remote compactor, which is shown there in green. Operators would be utilizing signal remote equipment on their waist to run both the compactor as well as the slinger. And as I mentioned, we had a separate setup to utilize our Brock equipment to spray the M25 and verify such things as how long of a sweep did it take to apply it, how much would it build up in that timeline was sweeping, so we were able to, train our operators for real life condition when we got to the A-bays, which I'll speak to in the next slide. So the video on the right, obviously, is showing the execution of the A-bays work package, where we again sprayed the liner prior to filling the bays with an A gravel. Here the video is showing you right now the operator running the slinger, which is being fed by a traditional dump truck of gravel. Once we do a certain set of lifts, we're able to run our compactor and verify the thickness as we go with our gauging system. Obviously, the intent to do with the filling the bays and lift is to ensure structural integrity remains in each of the bays as we do our lifts. There were a lot of prep works, as I mentioned, to do. We didn't complete the spraying. We had SSC removals to do. We had to put the Haskell barrier in. We did run some challenges with the slinger and its ability to reach. So the team did an exceptional job pivoting to the use of a localized crane and the hopper to gravel hopper into those hard to reach locations where the slinger just productively couldn't make those tight corners. Slide, please. So the J bays were the second bays that we were challenged with. We took a lot of lessons learned from our first A bays campaign and applied it here to the J bays. So due to some challenges with location, we were unable to utilize the Baroque in the same manner we did with the A bays to spray these walls. So our field technician team came up with innovative ways to spray the walls using a rail system. So the sprayer would essentially mount a rail system. It would move up and down its track, providing the appropriate coating, which we also did mock-up activities for. What isn't present here in the picture is upon completion of spraying the M25 polyurea, the team has a drone that had remote survey equipment on it and is able to essentially fly the drone throughout the bay to showcase that the spraying has essentially achieved its intent, signifying how much contamination control it was successful in achieving. The other challenge here was that obviously the bays are long in length and there's a barrier in between. So we had to come up with a strategic way of moving gravel from the exterior, where you can see the two windows on the far picture, into that far bay, which is sort of outside the remote slinger's full capability. However, the team did some practicing, built some confidence, came up with some contingency plans, and were able to successfully fill the bays based on the plan and the methodology we used in A-bays. Finally, the last challenge, which we'll get into in the video here, but the J-bays themselves have two locations, which we call surge tanks, which were feeder tanks for the deionization system in the adjacent facility. They were unable to be filled with gravel, so the team came up with a really innovative approach by finding creative ways of getting a pumper truck in to pump those areas, hard to reach areas with grout. Slide, please, Mike. So here's a great visual of us using our drone from the innovation team. There's our Baroque with the sprayer attachment on it. And you can use the drone again to verify an adequate coating in all locations to ensure we met the intent of, one, the spray and thickness that we want to achieve, and two, there's again a dose rate instrument on on that drone, which allowed us to verify if we were able to, stop some of that contamination spread, seal up those areas of concern, and know what we were left with as an end state before we filled in space. So last of the significant bays is the X bays. So the sorry, Mike, what's slide on here? Slide. So the
24.
Yeah, thank you. The X bays area was inaccessible with the remote slinger, which is one of our first problems. We don't have any close windows, and the X bays are significantly larger in size than the A bays and the J-rod bays. So we had to look into alternate solutions for sealing and shielding due to, again, high contamination and dose rates. The complex geometry of the area required the Brock robot for spraying. However, there's lots of blind spots that we were unable to see the equipment once we deploy it for the M25 spraying. And the lack of detailed floor loading analysis required us to do some assessment for how we could place a crane in order to drop the robot, the Brock equipment index base for the activity. And the planning phase involved collaboration between our innovations team, our planning team, our field staff, our health physicists, our engineering team, and one item that supported us in our planning activities was we worked with our innovation team to mount a 3D scanner onto a robot dog and have a custom contamination suit made for the dog. As these are quite expensive pieces of equipment. We want to ensure that we can utilize them in other facilities. So the field engineering team designed 4 protections post this 3D scanning to support this facility-wide gantry that was used to deploy our Brock into play to help support the spraying. When we complete the spraying, we were going to have to go back to the grout methodology as I mentioned. We're challenged with loading gravelness locations, so identification of a need and a way to deploy grout has been and still is something that the team is working through. However, we're just ready to start executing now. And maybe I'll switch to the next slide, Mike, so we can get an idea of how great our robot dog scanner did for us. So mounted on top of that robot dog is a 3D scanner, which gave us basically a full map of the bays themselves, which, as you can see here, loaded into the bay, informed us of these hard to reach locations, size constraints for moving the Brock equipment down. And as you can see, we were faced with these challenges where there's these little ledges and dips. So having this kind of information to inform planning really took a lot of the guesswork out of and the assumption work out of the team's hands, and right into their computers. And there's the finished product of the 3D model, which we can use and manipulate. We can get distances and measurements off it. So since that work, almost roughly a year ago, we now have our full plan. We're just weeks away from beginning the spraying activities here. And then we'll be moving into, deploying the CLSM grout into the actual bay to finish off that area. Here's some great videos of both the rail system, the J-rod bays, and previously with the Brock utilizing its arms itself to deploy the M25 polyurea spray coating. There's a great visual of the drone with its protective cage prior to it being deployed into the J-rod bays here again. Yeah, that really wraps us up here, Mike. I want to thank everybody for participating today in this webinar. Again, I'm really excited to share some of the innovative ways we're overcoming challenges both in the nuclear industry as well as in our decommissioning of our facilities here at Chalk River. I want to thank the staff who support us in all of our endeavors, both directly in the field as well as our innovation team, our field tech team, engineering, our SMEs from OS, RP. They do a fantastic job every day, and I really appreciate how they are able to think out of the box and look at some of these innovative approaches to make it safer for us to come to work, but also to look at efficiency gains we can make here in the field for both CNL, ACL, our client, and obviously the environment and the community around us.
Okay, great. Thank you, Patrick. Great presentation. Some really innovative stuff you have going on, and quite a busy time for your group. So now you can ask questions through the Q&A function, and we will get started here. Can you give us a sense of dose fields before and after your mitigation?
I'd rather not attempt to guess and provide you what we're able to achieve with the activities for both spraying and shielding of some of these bays. I'm happy to share some of those percentage drops, probably not by the actual data, but we can probably say, we've reduced fields by 80% in many locations, maybe even more. And Mike, if that's an acceptable approach, probably the best versus me trying to guess dose rate droppages.
Yeah, and we can also do written responses, whenever we send out the links to videos. So if anything asks for any technical response, we can always give them a written response or give them percentages. Or
I'm confident to say we're in the ballpark of 80 to 90% reduction when we complete the spray and the filling activities. So again, taking readings over top of the bays to now when we fill them allow us to actually stand on top of these bays safely without significant dose work.
Okay, so what type of work are you going to be doing once you're able to work atop of these bays? Is it decommissioning, like removal of?
Yeah, great question, Mike. There's lots of services that still run along the ceilings of the building. So your general building services, be it HVAC, be it plumbing, be it active drains, those all now have to be, characterized, removed, and waste packaged accordingly. And then it also is a lot of this work is in preparation for the removal of the upper structure. So we don't want to be working above and demolishing a building and having debris falling into these open bays. So by shielding them and capping them, it allows us to remove the upper structure to then focus on the second phase or second campaign in the future for remediating the actual concrete in the bays themselves.
Okay, great. Thank you. Okay, go to our next question here. Can you explain what M25 polyurea is or what it's compared to?
The simplest term I can utilize is people spray these applications on vehicles in box liners. It is a very hard product that essentially has sort of it's tear proof, it's impact proof, and it can basically withstand significant pressure, hence why we're filling with grout and gravel against it. Simplistically, I'd say it's similar to like a bed liner, but it's definitely more of a rubberized product, especially when you layer it at a quarter-inch thick.
Okay, thank you. Working with drones and robot dogs and a lot of a lot of cool machinery and getting in some some tricky places. Were there any surprises or particular challenges working with this kind of stuff?
Yeah, great question. Thanks. I think I tried my best to indicate, for instance, in the X-Rod bays, um, we found locations where we realized that some of our original planning wouldn't work based on the structure of the building. So, there's some slanted alcoves, there's some tanks, or those surge tanks I mentioned, the J bays. By doing those pre-inspections, that verifies what we're seeing on 2D drawings, which again, as you can imagine, are probably quite old. And so getting sort of a live perspective of what we're looking at really helps inform planning. And then when we get into utilizing equipment, I mean, maybe the only challenges we face is, when you put them into that full application or the full execution, sometimes they don't perform exactly as they do in the mock-up. And again, that's due to just the continuous wear, the continuous effort we put on our equipment. But we plan for that. We have contingency equipment. We have extraction plans. All those things are planned and taken into account.
Okay, thank you.
I hope that answered that question, Mike. It was a bit of a broad one, sorry.
No, that's good. Okay, couple more here coming in. What kind of technical skills does the team have to do this type of work?
Great question. So our field technician team, who run a lot of the equipment, or the innovation team. Maybe I'll start with the field technician team. So the field technician team who run the robotics, run the spraying systems. A lot of them come from trade backgrounds, but this stuff isn't sort of common as a routine practice in the industry. So as I mentioned, when we take on new technologies, we spend extensive time researching the equipment, talking with the suppliers, understanding how they work, understanding their failure sequences and scenarios. And we get to the mock-up. We do training and training and training, practice and practice and practice. And then we always talk about, failure scenarios. What could happen to this equipment while we're using it? What do we need to plan for, and how will we respond in that event? The second side is the innovation team. And again, they come from an array of backgrounds of engineers, ex-operators here in the reactors, guys who are just really into that, that innovative technology. And as I mentioned, they do a lot of that same approach. They work with the suppliers, they understand the products before they buy them. When they buy them, they do extensive research into their operations. They write their own operation manuals. They practice, and they practice, all in support of our training activities.
Okay, great. Thank you. We'll get to a couple more. Were there mostly fields, or was there a lot of loose and airborne contamination?
I can say for generally, it was majority was fields. There obviously is some minor loose contamination that was found, but again, we don't send workers down in these bays to take swipe samples for loose contamination. Again, it's just what we picked up on any remote tooling or the innovative equipment such as the robot dog. But remember that these bays, during their transition in the 60s, did go through a bit of a cleaning campaign. Some of them got their own floors poured in the bottom, so maybe a couple feet were poured in prior to them being repurposed after they were cleaned. So I'm going to say the fields were generally the challenge, where in some locales, and again, I'm not saying there's no loose contamination. In some locales, there were loose contamination, which we again were aware of and manage it through the application of the M25.
Okay, great. Thank you. Okay. Next one. What does repurposing shielding material as clean fill mean, and why is this beneficial?
Yeah, so again, one of the benefits of using the M25 and talking about any possible loose contamination, utilizing things like this CLSM grout and the A gravel, there's opportunities here now because these are lined that this material can be repurposed. If we do the appropriate verification, we could be using it for you're either layering in our NSDF, so repurposing existing material, or utilizing in other locations at Chalk River versus having to utilize it or call it a waste, because we've done everything in our power to keep that material clean. So therefore, it can be repurposed versus being considered a low level waste, which we want to avoid.
Okay, great, thank you. Let's go for a couple more. It means it was a good presentation, Pat, because we have a lot of questions.
Great, or I left it on hold, one of the two.
A decontamination question about the robots you use and drones. Is it hard to decontaminate them for reuse, or has that become a problem?
Again, luckily, based on both applications, I mean, the drone itself is flying loosely, and the cage itself may come into contact the odd time, or if it were to ever, fall to the ground, the cage is easily either able to be decontaminated, so wiped down and re-verified, re-inspected by our radiological staff. Same with the robotic dog. Again, we put the barrier on it, so some of the main controls and the intakes for the motors wouldn't get contaminated was sort of a strategy. But wiping down the feet of the dog is not a challenge for our radiological team. They decontaminate much more challenging components here on site than those two items. However, some things are considered consumables and waste, and that is just a cost of doing business for us.
Okay. Speaking of business, any future plans of going commercial with any of the applications? Any other nuclear facilities other than CNL taking notice of any of this kind of stuff?
Great question. I appreciate whoever asked that one. I mean, we do have a commercial team here, sort of standing up at Chalk River, who does keep a close eye on the execution work we're doing, both in our operating S&T lab as well as our decommissioning facilities. And when they do network with our nuclear industry partners, they do convey some of the great work we're doing at Chalk River, which then spikes interest. And the hope is for more requests for support commercially that some of our partners, such as OPG, Pickering, Darlington, or Bruce in Port Elgin. So the answer is yes. I think folks know what we're doing here. We do our best through these webinars and attending conferences to share some of the innovative things we're doing, and our goal is to someday soon support some commercial initiatives.
Okay, awesome. We'll give you a break now. I know you said you're feeling a bit under the weather earlier, so well, I think we'll end it there. So any questions we didn't get to, we will respond to in writing, along with a link to the video. This will go to everybody that signed up for the webinar. When we post to YouTube, we'll send the links and all the answers to everybody. But before we wrap up, just want to remind everybody to please complete the follow-up survey that we'll be sending out shortly after today's webinar. And once we do send out follow-up emails with the YouTube link and the answers, feel free to distribute it to anyone who might be interested. If you have any questions or want to get in touch, please email us at ermstakeholder@cnl.ca. Thank you, Patrick, for a great presentation. Lots of great stuff going on in your realm, and happy to help you present that to the general public.
Thanks, Mike. I think these webinars are a fantastic way of showcasing what we're doing at Chalk River, and I appreciate everybody who attended today.
Okay, awesome. Okay, everybody, that wraps it up. Thank you, and have a good day.
Thanks.